All right, welcome back to another exciting day of Algebra 2. Today we are talking about rate of change, which we normally associate with slope, and that formula y2 minus y1 over x2 minus x1 is still what we're going to use to find the rate of change, but we are going to be looking at rate of change not just for linear graphs or functions where the rate of change is constant. We are actually going to also look at quadratics and piecewise and all sorts of things where the rate of change might be different in different places. So what we're going to kind of do first is refresh our memory on what would indicate positive, negative, or zero rate of change. Remember, positive would mean something's increasing, negative would mean something's decreasing, and zero rate of change would mean we're staying constant. So we're going to look at these different graphs and scenarios and indicate if it's positive, negative, or zero rate of change. So, for example, the change in temperature of a liquid in a cup of coffee, a cup of hot chocolate left on the counter during the first 30 minutes after it's poured. Well, we know that it's probably going to start out hot, and over time the temperature is going to decrease as it approaches room temperature. So that is going to be a negative rate of change. Looking at this graph right below it, that is linear, and I would be walking downhill if I was walking across that graph, so that would be a negative rate of change as well. The change in height of a girl from 4 to 5, well, when you're that age, you are growing quite a bit, so we would hope that that is a positive rate of change. She's getting taller. Looking here, hours since 3 p.m. and the distance traveled. I started 30 meters away, and then I increased to 150 meters away. We could actually calculate this slope if we really wanted to confirm our thoughts, but this would be 120 over 4, which is 30, and that is positive, so this is a positive. The change in the number of guests in an amusement park over the first hour that it opened. Well, again, we would probably interpret that as being a positive rate of change because the longer that the park is open, the more people are going to show up. Looking at this graph here, that horizontal line has a slope of 0, so that would mean that we have 0 change. The change in height of a girl from age 19 to 20, this one you could kind of debate a few ways. Usually by that age, people are done growing, so for the sake of just stating the obvious, we're going to go with that's 0 rate of change. You could possibly argue it's positive, but more than likely not negative. Looking at this graph, it's not perfectly linear, but it is increasing for the most part, so we're going to call that one positive. The next one is part of a quadratic, and we are walking downhill, so that would have a negative rate of change. And then the change in the number of guests in an amusement park during the last hour of the day. This is as opposed to the first hour of the day. In the last hour of the day, people are going to be leaving to go home, so that would be negative. Okay, moving on to another example where our rate of change is not the same for the entire graph. Let's say you take some public transportation like a bus near your home to go to the park, and the park is 3.4 miles away, and your trip on public transport takes you about 19 minutes. The graph below shows the number of minutes since you started your trip at the park and the corresponding distance from home. So this is not all one function. This is multiple pieces together to represent, again, your distance from home over time in minutes. So we first want to identify an interval of time for which the rate of change is positive. Now that happens in multiple places here. Anywhere that I am uphill, I could use as my answer here. So any of those intervals, I will go ahead and write them all out just so that you see them all from 0 to, and these are in 2-minute intervals, so from 0 to 2, as well as from, sorry, that would be 0 to 4, not 2. My apologies. 0 to 4. Then from 10 to 12, 14. Then again, that's 14. That's 16 until 18. And then again around 20 until, we'll call that 23-ish. And then at 24 until, we'll call that 29. So over all of those intervals we are increasing. You don't have to list all of them because it just said to identify one, but any of those would be sufficient. And explaining what that positive rate of change means in the situation, well, that means that your distance from home is increasing. So, and it's not the same slope over the whole time, but it is positive, meaning our distance from home is increasing. Identifying an interval where the rate of change is negative. Again, that happens in multiple places. So we could go ahead and describe each of those intervals as well, but we've got 4 on this side also. And I'm going to list those out, starting here at 60 until 62, 64, we'll call that 65, and then it starts up again at 66 until we'll call that 69, and then again at 70 till we'll call that 73, and then the last interval is from 74 to, and you know what, that one is still also decreasing, it just changes by how much, so we'll call that 84. Okay, so again, multiple intervals, you only needed to list one, that's sufficient. And so what does this represent? This means that your distance from home is decreasing. So when your distance from home was increasing, you're getting further away from home. When it's decreasing, you're getting closer to home. So an interval where the rate of change is constant, and again, there are several here. 1, 2, 3, 4. Here's a really long one. 6, 7, 8. And those, some of them are pretty small, so I'm just going to go ahead and list our longest one, which is probably when you're at the park. So this is around minute 28 until minute 60. And again, you could list those smaller intervals, but they're pretty tiny. And so what does that represent in this situation? That means that your distance from home is not changing. So you are staying put. So again, quick refresh on what this graph is actually showing. When we're positive rate of change, that means we are headed to the park. These little intervals of no change probably represent bus stops if we're on public transportation. This longest interval is likely the time we're at the park. And then this is our ride home. Again, these rates with no change would mean that we're at bus stops again. Okay, moving on. We are looking at Karen running a marathon. And we've got her distance at all of these different starting points. So we've got these intervals A, B, C, D, E, and F. And so what we are going to do is look at her time and distance at the start and stop of each of these intervals to fill in this table. So A starts at 0, 0, and it ends at 1, 6. That's where B starts, and then B ends at 2, 9. That is where C starts, and then C ends at, we'll call that 2.59. And then again at 2.5, sorry, that's where C starts again, 2.59, and it ends sorry, okay, that was where A starts and stops, B starts, C stops. Okay, now we're looking at where D stops, that's 4:18. And then E goes from 4:18 till we'll call that 4.518. And then F is going from 4.518 until we'll call that 6.5. And we know she's running a marathon. So she stops just shy of 27, so that probably means the 26.2 miles that are in a marathon. So during which interval was she running the fastest? Now, we could do this mathematically, or we could look at our graph to give us an indication on what the actual answer is and use math to verify it. So where she's going to be running the fastest is where my rate of change is the greatest, aka my slope is the steepest. So I can look through here and kind of see, A looks pretty steep, steeper than B for sure. D is also pretty steep, and so is F. So let's look at the slopes at those 3 intervals and see which one is the greatest. So starting with A, the slope at A, that's going to be 6 minus 0 over 1 minus 0, so that is 6. We have a slope of 6. Looking at C, I am going to, this is interval D. We are ending at 418, so that's going to be 18 minus 9 over 4 minus 2.5, and that is 9 over 1.5, which is also 6. So those actually have the same slope. So let's look at our last increment F to see if it is any larger or not. So F, that's going to be 26.2 minus 18 over 6.5 minus 4.5. And that is 4.1. So that is actually the slower slope. So A and D, she is running the same speed. So interval A and interval D are her 2 fastest speeds. So where is she running the slowest? Well, we already know those 3 intervals. Let's look at B and confirm if it is any slower than F. So if I'm looking at B, that is going to be 9 minus 6 over 2 minus 1. So that is 3, and that is the lowest slope out of all of those. So she is running the slowest over interval B. Where was she resting? Well, that's going to be all the intervals where her rate of change is constant. We have those horizontal lines. That is at interval C and interval E. And we could calculate the slope there to see that it is a slope of 0. So what was her average speed for the entire race in miles per hour? Well, we know she ran a whole marathon, so that is 26.2 miles, and the amount of time it took her was 6.5 hours. So that is approximately 4 miles per hour. Now, runners often will measure their time in minutes per mile, or how many minutes it takes them to run 1 mile. So if we wanted to calculate that, minutes per mile, that means that minutes is going to go on top, so I need to convert 6.5 hours into minutes. So 6.5 times 60 is 390, so 390 minutes, and our mileage is staying the same, that's 26.2 miles, and that gives me approximately 15 minutes per mile. Okay, and we are running low on time, so I'm going to pause here and create a second video for the rest of this in a part 2.